Hi, my name is Dennis, and this is for the TA demo video. And I'm going to demo a problem inverting a binary tree. We are going to find a algorithm and also the time complexity for the algorithm. First of all, we have to define the meaning of a binary tree and also define the meaning of inverting. Here we define a binary tree rooted at node T, as every node in such a tree has at most 2 children. Here are the pictorial illustration for binary tree. Um, these two, although they look like a linked list, they are also a binary tree because we define a binary tree very broadly, where every node in this linked list has exactly 1 children, which is less than 2. So these two are binary tree. And then each node also has 2 pointers, which indicate the left child or the right child, which the pointer value can be the node or it can be null. Second of all, we are going to define the meaning of inverting. So here we define inverting that every node in the tree, the right node and the left node are being swapped. So here is a illustration of what that means. For the second one, the left child becomes at the right side of the node, and then for this node, it becomes the right child of this node, which it was the left child of this node. For this one, the right child of the root becomes the left child of the root. The left child of this node becomes the right child of this node, and then so does this one. Usually, when developing an algorithm for a tree, we want to use some kind of recursion because a subtree of a tree is also a tree. Therefore, an algorithm works on a tree must also work on a subtree. We can use DFS or BFS, and then here I'm going to argue that the order of which we traverse the nodes doesn't really matter. So basically, we are just swapping the left pointer with the right pointer. So here is the core of the algorithm where we do the swapping. The first couple of lines are the base case. If we were inverting a null node, we're just gonna return. And then here is the recursive part. We are visiting the left child first and then the right child. For example, if we have a tree like this, first of all, we're gonna call invert at the root node, which is the node 1. And then we call invert 2 and 3. And then the recursion will pop the stack and we first execute invert 2. Invert 2 is going to be at this node, and then we are going to swap the left pointer and the right pointer. So it becomes 5 and 4 rather than 4 and 5. And then we are going to call invert for the node 5 and 4 on the stack. And we pop the stack, we call invert 4. Invert 4 also has 2 nodes, the left node and the right node. However, both of the nodes value are null, so we're just gonna return for these 2 functions. And then the same thing for 5, where 5 will call invert right child and left child, which both of them are null. And then we will pop the stack to call invert at 3, which is going to be the same process as this whole process. So here is what the tree look like after we successfully invert the left subtree, which is at the right side of the tree now. The time complexity of this algorithm is basically O of n, because we are traversing the tree exactly once, visiting the node, where n is the number of the nodes in a tree. I'm going to argue that it is the same algorithm for a binary search tree, because a binary search tree can be considered as a specialized case for our definition of a binary tree.